Welcome. This lesson we will see the application of partial differential equation, and we will look in the water resources engineering. So I will derive a differential equation from the mass conservation principle, and that basically would be the groundwater flow equation. This is just an example. You can drive the contaminant or heat transport equation would be something similar or other equation. Yeah. And then I will make some simplifying assumption and solve it analytically. Okay. So partial differential equation in water resources engineering, you will see a lot like groundwater flow equation, groundwater flow to well, contaminant and heat transport, Navier-Stokes equation. Navier-Stokes equation is a general flow equation for incompressible flow, and you can drive uh, from this equation many of the flow equation for pipe flow, open channel flow, even Darcy law for groundwater flow. You can drive it from Navier-Stokes equation. Yeah, you can. And all these, remember, based on very simple principle like increase minus decrease is equal to change. Like inflow, so here this is Q out is equal to Q in plus, plus or minus, yeah, change in storage over time. Yeah, delta S over delta T. This could be plus or minus. Yeah. Okay. And that, for example, like when we apply this very simple law of conservation to flow. Yeah. So we will let's just look at this and use this simple principle to drive groundwater flow equation. To drive the groundwater flow equation. So assume that we have a mass influx along the x-axis. So here, like mass influx along x-axis. So this is like my x-axis here. Yeah, this is my delta x you see here. Yeah, and then I have mass influx. So basically, mass influx along this boundary. Yeah. So you have this guy, like something is coming along this boundary. What this something will be? Remember, we have seen this before in the conservation of mass. I said like rho water Qx. Q here, this is flux, yeah. So this is Qx, flux density, and Q that has a unit of length over time. So that's like your flux that's entering. Okay. And that would be Q, yeah, time. This is like here. This is like my dy, yeah, and this is my dx, like what is entering through this volume basically. So that's like dy time dz. Yeah. So that would be the max influx, and that will have a unit of mass over time. Remember, we've seen this in the previous lesson when we were talking about the conservation of mass. So because why? Because remember, let me do this here. So rho, that is mass over volume, L minus 3, Q, that is L over T, flux, and then dy, that is L, and dz, that is L. So basically, this guy will go away with this guy, and then you will have mass over time. Yeah. So this is the mass influx, like my influx that is going across all this boundary here of my volume. So this is my volume, like here, this guy, I don't know why it does not point. Okay, this guy is my volume, and this is flux across this volume. Okay, so that is mass influx, yeah. mass outflow. So let's look at the mass outflow parallel here. So the mass outflow, which would be parallel to the x-axis. So again, this is my x-axis, and this would be coming out here. Yeah, the outflow. So this outflow would be what? So this would be like parallel, like a parallel x-axis. Yeah, or along x-axis or whatever. Yeah, along x-axis. That would be equal to the mass influx, like what's coming in and what is changing inside this volume. Yeah. So that again would be my what's coming in rho x dy dz, and whatever is changing inside this volume. And we've seen this before in the conservation of mass, if you remember, when we looked at the divergence theorem. So that would be parture over parture x. That is like rho w again qx. And this would be along the dx. Okay, so let me show you how this will look like. So let me clear these guys here. So that's like my dx, like here. That's my dx, my dx, my dx. And that is basically along the dx time like dy z. Like I'm looking at what is it changing across this volume. So basically that would be what is it changing. Oh, here, for example, yeah, you see this is, that would be dz, and this is dy for this like dx, and then the same, another one here, yeah. Oops. I guess this is correct, yeah. Like I need to look at the whole volume. This is like one here. That's basically what is inside this volume here. Like dx, yeah. So basically this is dy, this is dy, this is dz, and that would be like the dx, yeah. And again, if I check the unit of this, guys, what will I get? I will also get m over t, because here, let me do it like you want to do it. So let's, not the unit, I mean the dimension of this guy. So I have rho here, that's mass over volume. I have q here, that's L over t minus 1. I have this guy here, that's L cubed dy dl dx. And then over here, L. So L will go with the L, this guy will go with this guy, and I will get m over t. Yeah. So basically, I got this equation here. Yeah. That is basically my volume integral, like this. That basically my volume integral, like what is it changing inside like this volume here. Yeah. Let me delete. So basically, that is what is changing inside my volume here. Okay. So if we did like subtracted this guy from this guy, yeah, the mass inflow from the mass outflow. So basically this guy will go away with this guy, and I will get something like this. My parture over parture x rho w q w dx time dy time dz. And what would that be? That would be the mass accumulated. That is like mass accumulated or mass accumulation within control volume. Yeah, that's the math accumulation within the controlled volume. That would be this term here. Yeah, but remember, this is just like I'm only like in this what I showed you here. I'm only considering qx, like q that's coming from here. But I also have qy, q that's coming from here. I have flux that's coming from here. So sorry, this is qz. I have qz, q that's coming from here, and I have qy, q that is coming from here. That's qy. So my total flux actually, like what is coming in this volume is not only coming from x, it's coming from x, it's coming from z, and it's coming from the y direction. Similarly, it's leaving from x, it's leaving from z, and it is leaving from the y direction. Yeah. So I can do like whatever I did here, I can do the same for like the other two dimension. For I can do the same. So as I did it with respect to x, I can do it with respect to qz, and I can do it with respect to qy. So if I did this, that will give me my total mass accumulation basically. So if I did this, that will give me, I can take the negative sign out here, and that would be parture x rho w q w dx dy dz. Yeah. Let me take this guy out as a common factor. So I will take like this guy out also as a common factor. So that would be plus parture y rho y q, sorry, this is qx qy plus parture z rho water qz. Yeah. So I got something that looks like this. Yeah. And that would be dx dy dz. Yeah, dx dy dz. So I got something that looks like this. Yeah, that's okay. Yeah, so this is okay. And now remember Darcy law. I have like q is equal to negative k. Yeah, dh over distance ds. Yeah, so I can substitute basically like this q with like qx, qy, and qz. So I can substitute this guy here. So if, like here. So if I did this, then I will get something that looks like this. Parture x rho w and qx that would be negative. So the negative here will go away with the negative here. So I will not write it. So I'll just get rid of this negative, and that will go away with the negative here. So that would be del qx, that would be k in the x direction, and delta h over delta x plus something that looks like this. Yeah, plus parture y, that would be rho of the water, k k is the hydraulic conductivity, so k is the hydraulic conductivity, the h over delta y, yeah, plus, I don't even need this guy anymore, plus parture z, rho w k z delta h. Actually, this shouldn't be, this should be also partial. Parture should be partial derivative is not a total derivative. Partial over parture z. Yeah. Okay, so that's basically. Does this look familiar? Yeah, it looks familiar. This is like the divergence theorem which we did before. So I got an equation that looks something like this, and this is equal to what? This is equal to the change of mass within the control volume with respect to time, which, so basically like this guy is, like this is equal to the change of mass with respect to time. Yeah, that's basically what this is. That's the change of mass with respect to time. I can remember I can represent like so. Rho is equal to mass times volume. So I can represent, sorry, mass, not time volume, mass divided by volume. So I can represent mass as rho times volume, and then I can represent mass as now here, let me tell you something, like the mass here, the rho of water, this is in porous media, so water is not everywhere. So like this is like your porous media, let's say this is grain size, like these are some grains here, like some sand, gravel, silt, clay, whatever. So these are your sediments here. And the water just occur in the fracture of these sediments. So that's where the water flow. Like water is not flowing everywhere, it's just flowing within the porous media. So I will add my volume here, which will be like dx, dy, dz. And then I will add porosity. So porosity that account for pore space where water is flowing or is occupied by water. Not necessarily flowing, but is occupied by water. Okay. So that is the mass. So I can just present this one. So I can say that's equal to parture rho water time my porosity time my volume dx dy dz. That is over t. Yeah. Okay, so now I have an equation. Yeah, now basically I have an equation. I have an equation for the change of mass with respect to time is equal to uh, this three accumulation term, like this three, which are the volume integral, which we know that this come from the diversion theorem. Yeah. So we know this. So one thing we can do for simplification. Oh, sorry, I forgot to put here one term. That should be dx, dy, dz. Remember, like this guy here should be here. I just got rid of the negative, but still this guy here. So one thing we can do, like to simplify this equation, like this guy can go away with this guy, and then I will only end up with these guys. We can also assume that the density is constant, like the flow is uh, or yes is we can take like let me or let's just take this w out here, so we can assume that this is constant, so I can put like this rho w here, density of water here. Yeah, it's not like changing within space. So here I can get this like this equation here, which is basically 1 over rho w n. Yeah, and parture t, and then I will like divide this. I bring this term here divided by this guy. That is equal to parture x k x x parture h parture x plus parture y k y parture h over parture y plus parture z k in the z direction parture h parture z. Yeah. So I can get to an equation that looks something like this. One more simplification I will do. I'm not going to show you like, I mean, this is not a groundwater class, but I can replace this guy by, like I can replace this term by something called like specific yield, specific storage. So specific storage that has a unit of 1 over length. Yeah. So I can replace this guy by something called like specific storage. So I will have specific storage departure H, and then I put like here's a hydraulic head here is equal to like these guys here. Yeah, it's equal to this guy is here. So basically, this is the derivation of the groundwater flow equation. Drive it based on the uh, principle of the conservation of mass. If you took the groundwater hydrology class with me, you will find that in the groundwater hydrology class, I have a different derivation for this equation, much simpler derivation for this equation because I was not driving it from the conservation of mass principle. I was doing something much more simple. Again, of course, from the same principle, but in a much simpler way. But here, I wanted to show you this so that you can see like the surface integral, the change in inner volume, and then you can relate this to the previous equations that I showed you for the conservation of mass and the fundamental theorem of calculus. And that's why I showed this derivation. So let's look here at those. This is the equations that we got here. Yeah, so let's look at it. So basically, this equation is telling me uh, the change in hydraulic head as a function of time is equal to the change in hydraulic head inside my control volume. Okay, this is in a confined aquifer. Confined aquifer, this is an aquifer that has a water table that is direct in touch with the atmospheric pressure versus unconfined aquifers is confined aquifer. I said the opposite. Confined aquifer, this is an aquifer that does not have like a water table. It is not in touch with the atmospheric pressure versus this one. This has a water table and it's in touch with the atmospheric pressure. I mean, this is not a hydrology class, so these details are absolutely not important. I don't expect you to know them or understand them, but just look at the derivation. Like what I expect you to see here is like see this derivation and how it relates. How I could this equation basically is the equation that is the base of groundwater flow model. So you have different groundwater flow model such as mud flow, that's a finite difference model, or fee flow, that's or sutra, these are finite element model. All these model, what they do is that they solve this equation numerically. So mud flow will solve this equation using a finite difference method, numerical method. Fee flow and sutra, for example, will solve this equation using a finite element method. Like this numerical method, we will cover them in the next module. But here I just want to, so basically this equation that you see here, this is the base, like mud flow solves actually this equation. Yeah, that's the equations of mud flow solve and all these models solve. Yeah. So this is equation is base of any of these groundwater models. And if you want to learn how to collect data from the field and set up this groundwater model and calibrate them, you can take the groundwater hydrology class. That's where you will learn this. But in this class, I just want to see you like the main equation for this model and where it came from and how it just come from something very simple, which is the laws of conservation. And if you want to put it mathematically, that could be described by the fundamental theorem of calculus. That's basically what I want. I want you to learn here in this lesson, this conceptual understanding, because this course is mainly to develop this conceptual understanding and fundamental skill, which we are developing here and learning here. Okay, so this one, let's review what we did before. I mean, this lesson is getting long, but that's fine. I can make some long lessons. Uh, because it's important. Yeah, let's review what we did before. Is this ordinary or partial differential equation? So this is a PDE. Why this is a PDE? Because I have my independent variables, not just one. I have multiple independent variable, which is x, y, sorry, which is x, y, z, and time. So I have like x, y, z, and time. I have like 4 independent variable. Okay. Is it linear or non-linear? Well, h here is linear, h here is linear. So my dependent variable, which is h hydraulic head, H here is linear, H here is linear. So is it linear or non-linear? It is linear, yeah? So this is like linear, okay? Is it homogeneous or heterogeneous? I don't see any source or sink term here with respect to my independent variable like x, y, and z. So it is homogeneous. Is it first order or second order? Oh, I see second derivative here and here and here. I see first derivative here, but it doesn't matter. If I see a second derivative, then it is like second order. So this is the second order linear and homogeneous partial differential equation for the confined aquifer. For the unconfined aquifer, we can, as you can have the Dupuy assumption, basically that head is not changing vertically, so head is constant in the along the z direction. So this is z direction. The head is not changing vertically, it's constant, and basically like just we have like this horizontal flow, so we can get rid of this term. And in this one here, the head is a function like of its derivative. So here we got this like head, like you see here, versus here. Here head is a function of its derivative. Here the specific yield was changed by something with, sorry, specific storage was, so specific storage has a unit of 1 over L. Specific yield has is like that's like volume over volume, which is like dimensionless. So this is dimensionless. So you see that's the difference between like these two equations. Yeah. So both of them has like, remember we in the first lesson we talk about dimensional homogeneity. Yes, all these terms, if you check the dimension of this term, 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 all these terms will be will have dimensional homogeneity. Yeah. Okay. So let's look here. Okay. So here, can we classify this equation? That's the same. That's like a PDE. Is it linear or non-linear? No, it is non-linear. Why? Because I have the h, the function, and its derivative. So this is like non-linear. It is homogeneous. Yes, it is homogeneous. It is homo. And it is second order. Okay. So let's look further at this equation and let's try to make some simplifying assumption for this guy, yeah, for this equation here. So let's look further at this equation and let's do some simplifying assumption. Get rid of this. Let's do some simplifying assumption, yeah. So here, this is the flow. This is the groundwater flow equation for an unconfined aquifer with this specific yield term. Basically, it's telling you the change of head in time is equal to the change of head within your domain, yeah, your aquifer. Isotropic means that K, like, see, this is my hydraulic conductivity. Let's say this is I'm looking at one cell, yeah, in this model, yeah. So Kx means that the hydraulic conductivity in this direction is different, and Ky, it has like different hydraulic conductivity. So here it will has one hydraulic conductivity, here it has another hydraulic conductivity. This is Kz, yeah, and so on. But if my hydraulic conductivity is the same in all direction, then I could just get rid of this guy because it's the same. It does not change by direction. So if I measure the hydraulic conductivity in this direction and I measure hydraulic conductivity in this direction, I found the same. They don't change by changing the orientation. Yeah. So then this would be for an isotropic. So I can have like this term here. Another simplifying assumption, like let's say my hydraulic conductivity here has a value, and in the next cell, let's say K1, yeah, and then in the next region or cell or whatever, yeah, it will have like K2 here. Yeah, so this is K1 and this is K2. So this means that exactly what it says here is that partial, like partial x K. The K is changing with X. Here also K is changing with Y. Like if I go in the Y direction, K is changing with Y. This means because my subsurface is heterogeneous, I have different materials, sands and clays and gravels and whatever. So my hydraulic conductivity is changing. But if I have a homogeneous aquifer, like this is my aquifer, like let's say here, just making, yeah. And K is here is consistent anywhere, consistent everywhere. So this is homogeneous. Then basically K is no longer changing with X. So partial K with respect to partial X, that's equal to 0. This is K is no longer changing with X. So which means that I can just get this guy out. Yeah. Because it's no longer changing with Y, it's no longer changing with X. So for the isotropic conductivity, where conductivity does not change across the space, I can get this K out. So now you see what you are learning here is how to read and interpret like these equations. Like when you see K here, what does this mean? This means that I have this parameter which is changing in X and Y. That makes my equation very difficult. And that's why mud flow and free flow and all these things, they cannot solve this. So there's no analytical solution because K is changing in inside my domain. It's not constant. So that makes that there's no analytical solution for this equation. But if I got the K out where like K is constant, then that simplifies the problem. So I have something that looks like this. Yeah. Now let's do one more simplification. Let's assume that my Q in is equal to Q out. That's like steady state, yeah? Or like, yeah, here, or small q, doesn't matter. Small q, or see, that is a steady state, means that this is, there's, my head is not changing with time because it's a steady state. There's no, the change in storage basically is like equal to 0. Like the change in storage inside, like, so there's no like a change in time, yeah? Then I can get rid of this guy. So here, assuming a steady state where inflow is equal to the outflow with no change in storage. Now, so I simplified this like this. Let me make one more complication. Can I make one more complication? I will say, so now this is like the steady state, so it's not in steady, it's not in, I will make one assumption that there is, so this is like it's not in a transient state, it's in a steady state, that there is a change in storage which is like W. W here, that is like a source and a sink term. So can I add a source and a sink term here? Yes, I just want to add that source and sink, for example, could be recharge. So I could have like recharge here. Yeah. Oh, that is my boundary. So I could have like recharge here. I could also have pumping. This would be like this source and sink term. So I could have pumping here. I could have pumping here. Could have recharge everywhere. That's like up to me. So I can make this assumption. So I will move this and I will put this equal to 0. Yeah. So then I have this equation here. Can I simplify this guy a little bit? Let me look at this guy here. Yeah. This is, what is this guy saying? So this guy is saying like H partial H over partial X. Can I just multiply these two together like H times this? Like, can I say this is equal to partial H squared over partial X? So let's see how much you remember from our previous module, which is differential calculus. We didn't cover this exactly, but we cover problems that are similar to this. Like, can I do this? Is this correct? Or I have a mistake here? Actually, I have a little mistake here. I mean, it's almost correct, but there is a mistake here. Let me show you my mistake. Let me let me let me just show you like why this guy is almost equal to this guy, but there's some factor missing here. So let's just remember what we did before. Do you remember what we did before, like the chain rule and these things? So basically what I can say like my U, is equal to h square. Yeah, I will just show you that these two guys are, there's something missing here. Yeah, I will show you what is missing now. So I have like partial u over partial x. Yeah, and that's equal to what? That is equal to partial. Uh, so I have this here. Yeah, I have partial, like I will say like u is equal to h squared. So I have like partial u over partial x. That's equal to what? That is equal to partial u with respect to partial h and partial h with respect to partial x. Yeah, do you agree? This is a chain rule because this guy can go away with this guy. Yeah. So can we do it? So partial u with respect to partial x, that's equal to what? So here, like partial u with respect to partial h, that would be 2h. Yeah, do you agree? Like that would be 2h. So I could put like 2h here and partial h over partial x. And what is u? U is h squared. So partial h squared over partial x is equal to 2h squared partial x. So this is what we want, like partial h over partial x is equal to what? That is equal 1 over 2 partial h squared over partial x. Yeah. So is this guy correct? Almost correct. I just need to put like 1 over 2 here. Yeah. So basically, that I can, so I can just like simplify this. Yeah. So basically, what I can do, I can say, I will just like replace this guy with this guy here. Yeah. So that would be, I can take also the k as a common factor. So and I can take this half as a common factor. So I can say like, so you see here, like I'm replacing this guy here with this guy. Yeah, that's what I'm doing. And I will take this guy. So I will say 1k 1 over 2, and that would be equal to partial x. And then I will put here, I took the 2 as a common factor, yeah, partial h squared over partial x, yeah, plus partial y, and then I will say partial h squared over partial x, and that would be equal to my w. Actually, this is not correct because the w should be here. So I did a mistake here. That's plus w, that's equal to 0. So I will leave this 0, I'll just put the w here. So I will say this is plus w is equal to 0. Yeah. So can I combine these guys, like just combine like this guy and this guy to get my second derivative? Yes. And can I just take this guy to the other side? Yes, I can take this guy to the other side. So basically what I can do, I can say partial square h square over partial h square, yeah, plus partial square h square partial, sorry, there's a typo here, this is partial y over partial y square. That is equal to what? That is equal to minus 2w over k. Wow, so I was able to get something that looks like this. When this is equal to 0, when there is no like recharge, yeah, when there's no recharge, like when this is equal to 0, this is called Laplace equation, except for Laplace equation, it has like a heat here. It was like for transport, like heat transport. And I will show you like how to solve Laplace equation later. Numerical solution for this, yeah. Here with this term here, this is basically tells you this is the ground water flow equation in a steady state when you have a recharge term. Yeah, that's like abstraction, like recharge or pumping or whatever. Yeah, the sign will change. Yeah, but that's basically the equation that we have here, and let me just show you. Need to get rid of this. We need to get rid of this. Need to get rid of this. So let me just bring this guy here, make him bigger. Yeah. So basically, let's see how we are doing in timing. Timing is okay. I mean, this hopefully it will not exceed an hour, but that's fine. I've been making nice videos that are not long, so if I did the long one, that's okay. Okay. So here, that's the problem. Like you can apply, for example, like in this island, if you want to study the head, like the hydraulic head here in this island, in order to learn about the flow condition, where you can also use it to learn about drawdown or to estimate groundwater sustainability in this aquifer. So this is the equation here where without recharge term, like if you don't have like this recharge term, then you got this equation here, uh, which we can also write like this: partial x partial h square partial x square is equal to 0. This is in 1D, so here I'm just showing this in 1D. So that would be the case, that's like in 1D. So here, that would be like two rivers and you have an aquifer in between, or that could be like an island and you can have, yeah, two rivers in between or in the ocean or whatever, yeah. So that's like this example. And basically, I can know the head like this. If I solve it, the analytical solution for this guy is here, this guy. And I will show you in a minute how to solve this guy to get this analytical solution. If you have a recharge term, like this is without recharge. With recharge, like you have W here. So basically, like there is a rainfall here, 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 and this rainfall will infiltrate, and then this will like recharge your aquifer, recharge the water here. Okay, and some of this water, when there is a recharge, will flow in this direction, and some of the water will flow in this direction, and that would be like a groundwater divide. That's where you have the maximum head, and the water will flow here to this river or to this water body, and the other water will flow here and discharge to this river and this water body. And that's basically, you can learn about surface water, groundwater interaction, and so many things. Yeah. Uh, so this is when there is no recharge. When there is recharge, you have this term here, as hydraulic conductivity appears here. Okay. And we know that we can sorry, this is no 2 here. This is a mistake. Uh, actually, sorry. Let's remember here. Let's see what we have here. Uh, let's see. If I want to replace this guy here, let me, there's an error here. If I want to replace this guy here with this, uh, that should be, if I will replace this guy here with this guy, then I will have 1 over 2 partial h over partial x. Yeah. Uh, that's also partial x. okay, which means that there should be this two shouldn't be there, yeah. So you just get something that looks like this, yeah. So for this guy, yeah, this two shouldn't be there, yeah. Yeah, for this guy, this two shouldn't be there. It should be just like W, yeah, because of this, yeah. So you can either write it like this without like these two here, or you can write it like this. Oops, or you can write it like this: departure h square over x square negative 2 w, yeah, sorry, 2w. So let's just try to solve like any of these guys, yeah. Uh, okay, so I will I will here I have two examples. So in the example, I will solve this guy, yeah, and in the practice problem, I will solve this guy, yeah. What do I have here? Yeah, so in the practice problem, and I will do this in the tutorial. I will be solving this guy, yeah. So in order not to make this video long, so oops, in this problem, I will just solve this guy, yeah, and because I think we're already approaching an hour, yeah. So let me not make it very long. Okay, here we go. Let me see this guy here. Okay, let's look at this guy here. So basically, giving the governing equation of a steady state groundwater flow equation for an unconfined aquifer with H, where at x0 H is equal to H1 and at x is equal to L H is equal to H2. So x0, just like here, at x is equal to 0, H is equal to H1. So that would be like H1 here, yeah. And at H is equal to X is equal to L, like here, H is equal to H2. That would be the head here. So I have the head here and I have the head here. Okay. And I was basically asking you to solve this equation. So I have like an equation here, parture x, h, parture h over parture x is equal to 0. Yeah. So I have something that looks like this. And do you remember how to integrate this? Integration by part. Yeah. So we can do this through what we called like integration by part. So uh, let's do the first one. Yeah. So the first one, that would be parture. So I have to integrate the first left-hand side, parture x h. Uh, Here actually we don't need parture because this is now an ordinary differential equation because we have only one independent variable. So I don't need this parture. Like parture here, partial derivative and total derivative here basically will mean the same thing. Makes no difference. So I don't need to use parture. I can just use the total derivative. Yeah. That's like dx is equal to 0. Like I integrate the 0 dx. Yeah. So basically I do this integration. So if I integrated this left hand side, what do I get? So basically I know that this guy reverse this guy. So like these two guys are reversed by this guy. So if I integrated this left hand side, basically what I will get h dh over dx. And if I integrated this side, what I will get constant. Yeah. So that's basically my first thing. Then what we can do like a integration by part here. So now we can solve this with integration by part. So I need to integrate again. So that's delta h parture like c1 dx. So you see here. So let me integrate this. So remember like how to integrate this guy. So that would be like h squared over 2. Remember the integration? Plus here this would be c1x plus constant c2. Remember, like don't forget the constants. That's like plus c2. Okay, now I have some boundary condition. So this is my first boundary condition. This is my second boundary condition. So in my first boundary condition, x is equal to 0. I got like h is equal to h1. So can I do this? Yes. So I have here h square 1 over 2, and that's equal to c1, like this is 0 plus c2. So if so basically I have, that's like c2 is equal, so from this I get like c2 is equal to h square 1 over 2. Yeah, that's what I got. Do I have another boundary condition? Yes, I have at x equal to L, I have h is equal to h2. So can I substitute this? Yes, so I can h square 2 over 2, that's like c1 times L plus c2, and c2, that is, what is c2 here? That is like h1 square over 2. Yeah. So if I did this, then I can solve for c1. That would be equal to 1 over L h2 over 2 minus h2 over h1 over 2. Yeah. So I have c1 and I have c2, and basically I just like substitute them here in this equation. So what do I get here? So I get h2 h squared over 2, that's equal to 1 over L, and here I have h2 over 2 minus h2, sorry, h1 here over 2 times x plus c2, which is h2 over 2. So I got something that looks like this here. And if I want to solve for x, so I can just bring x, sorry, I want to solve for h, not h squared. So I can basically say h, the function of x. I can bring this like 2 here. I can simplify what is inside. That's equal to the square root of x over L h h1. This is like my boundary condition plus h1. Yeah. So now I have an equation that basically represent h as a function of x. So at anywhere inside, like here or here or here or here, I could know my hydraulic head. Yeah, which is basically, if I know my hydraulic head, I can substitute, I can know my flux, and if I know my flux, I could know about, for example, groundwater velocity, and I can do other things. Yeah. So here, this is a practice problem. Uh, this is a practice problem. Let me just I will, that's basically like I'm solving this guy here, yeah. I will show this in the tutorial section, how to solve this practice problem. And then basically, let's see here. I will show you how to solve this, and then I will like discuss the results and the meaning of this result. So try to solve it on your own, see if you can do it, and try to look at this results and the meaning of the results of this practice problem. Okay, let me do one more thing before I end. I hope I'm not exceeding an hour. Yeah, I will exceed an hour. I want you like, so this is the end of this calculus module. I just want to confuse you. Okay, so what I'm doing here, I am like I'm confusing you. So basically, I'm telling you, can you recover the original function? So I have here second derivative of like of this, and I have like two integral and two derivative, and I'm telling you, can you retrieve this function? So how are you going to do this? So here, the lessons that I want you to know here is that if you have a good, I mean, forget about this problem specifically, but this is the main message that I want to deliver from this example. If you have a good conceptual understanding of these concepts, and you will always not get involved into a lot of calculation and a lot of steps and get like dive deep into your problem. You will immediately find an easy solution. And that's the importance of having this conceptual and theoretical understanding. So for example, like if you take my groundwater modeling class and groundwater hydrology class, and I teach groundwater modeling, I tell the student that if you are an experienced modeler, your models will be very simple and your solution will be very simple because you have a very good understanding. You can put your hand on the problem and just solve it in the simplest way possible. If you don't have a good conceptual or theoretical understanding, you will be getting into a lot of details and a lot of calculations and a lot of experimentation and a lot of trials and error, and that's because you lack this good understanding or theoretical understanding. And this comes with experience, yeah, and with doing more. So if you are an experienced models, your models will be very simple because you can answer your question in the simplest and easiest way. So here, similarly, if you understand the fundamental rules of calculus, and I told you what is the original function here. If you already know that this derivative, they cancel like these guys, and this guy will cancel this guy because these are like the inverse, like this is the antiderivative. So this is the derivative and here is the antiderivative. This is the derivative and this is the antiderivative. So basically the original function here is x squared plus 1. That's the original function because I understand the fundamental rules of calculus. I mean, this example is stupid, but the meaning behind it is that if you have a good conceptual understanding, you will be able to do things very efficiently and very in the simplest way possible. If you don't have this understanding, then you will say, okay, I have this function, I will take the derivative of this function, so that would be like 2x. Then I will take again the other derivatives, that would be 2, and then now I have 2 dx. Then I will integrate, I will get a constant, then I will integrate again, I will get like 2 constant. Oh, now so I have like these 2 constant. What would I do with them? Like in order to solve for these constant, I need to have some initial or boundary conditions. So now, okay, somebody gave me this condition, like at f0, at x is equal to 0, my function is equal to 1, and at x is equal to 1, my function is equal to 2. So I substitute these guys here, then I got c2 is equal to 1, I got c1 is equal to 0, then I back substitute in my equations, and I got like x2 is equal to x1. Yeah. But somebody who understands the fundamental theorem of calculus, if you asked him this question, he will tell you the original function here is this guy. Yeah. So that's the lessons that I want you to know here. I will end this. Let me copy and paste this for you. I will end this lesson. So this is a good lesson. is the importance of having a good, like developing your knowledge and always learning more and more and trying to develop your conceptual understanding and not just plug some number into equation, but understand what you're doing, yeah, and understand the basic concept. So I will, having said this, here is the table. I'll just summarize it, what we have been talking about. What's the function? What's the derivative? What's an integral? What's the total derivative? What's the partial derivative? ODEs and EDEs. I'm not going to go through it. I will leave it to you to read. And I exceeded 1 hour. I think this is the first lesson since the semester that goes over 1 hour. That's fine. Next lesson would be hopefully short. So this is not like the end of this lesson. I have one more. Next lesson, I will just show you some more application of differential equation just outside these water resources, like some general application and uh, some other equation. Yeah. Okay, so I will stop here and I will like see you next in part 2 of the application of part